Hi, beg your pardon. My name's Sunny Vance, and beg your pardon. You can see a picture of me. I'm a senior architect at PingCAP. I've been here for almost a year and a half. I've been working on database internals since 2000, 2001. I mean, that's the only job I've had working on databases, but I've been working on databases from much earlier than that. I was the MySQL InnoDB team lead at Oracle, and as I mentioned, so last year I moved to PingCAP. So today I will talk about TiDB. So I would like to thank Ed for his presentation and telling us about his vision and the history. But I would also like to reiterate on some of the unique value that TiDB brings. So the first point is something that I would like to talk about from my own personal experience when I joined. It's really very easy to set up and start, and I was very surprised by that. All I had to do was download TiUp, run one command, and I had a full cluster going. And I was not used to that. I was used to starting up 5 VMs, starting servers manually, connecting this to that. It was very painful. So I would encourage anybody who hasn't tried TiUp to download it right now and give it a shot. It is extremely easy. So that really impressed me. It's MySQL compatible because MySQL is popular. People love it. We love it. It's not just, and so it's just a better MySQL in my opinion. That's the way I see it now. It's scalable by design because it's been architected from the ground up to be a distributed database. And this is an extremely important distinction when you compare it to MySQL. MySQL is great and it solves problems, but it needs very clever people to make it work at scale. It gives you like an IKEA kind of thing. It gives you the different parts and then you get your duct tape and you start joining it together and you make it run. It works. And people have done extremely clever things with it. And for one, I'm very impressed by the talent that has made taken MySQL where it is. It's very versatile. So TiDB is used from banks, some of the largest banks in the world, big financial institutions, large logistics companies, digital businesses like social media. So it works across all industries. So basically, anywhere you need MySQL, but then you need MySQL++, then it's a default choice in my opinion. It's very reliable. It is battle tested. I have seen stats where people have clusters of 500 plus terabytes running without any problem, which was a big surprise to me because of my background in MySQL. People have very large MySQL installations, but they are very different style. They're sharding. And there's a huge amount of pain in that. And most importantly, there is a very strong belief in open source at PingCAP. So it's like one of the, I would say, cornerstones of PingCAP's way of thinking and looking at software. And it's also important because it gets people to go and verify the claims that people at PingCAP make. Does it really work like this? Does it really do this? So open source helps. And then, okay. And you also get good feedback and patches from the community, which is extremely important. And you get better engagement. So what's the agenda for today? I will talk about partition draft KV, which improves performance. Internally, we call it multi-rocks, and you will get an idea of why it's called multi-rocks as I proceed. I will talk about resource control, which is about consolidating workloads, giving good QoS to your customers. And I will talk about DDL. DDL is one of the more painful things in a database. And when people talk in terms of terabytes, it causes a lot of pain to everybody. And in a distributed system, it causes plain square. It is extremely difficult. In a single node, it's fairly straightforward. So what are the changes we are making there? And there's a lot of work to be done, but we made some very good changes and exciting changes that I'll talk about. I'll probably talk the least about DDL because it has some very deep technical things which I would encourage people who are interested to come and talk to me after this, if they're interested. I'll talk about resource control in a little more detail and also multi-rocks. So you must have seen this reference architecture in our blogs, in different presentations. There was a variation of this in EdStalk. I would like to draw your attention to the boxes on the left-hand side, the TiKV node 1, 2, 3, 4. Why? Each of those TiKV nodes has one RocksDB instance, which manages all the regions. A region is an extremely important concept inside TiDB. So I will sort of get to what multi-rocks is, but keep that in mind. It's key in understanding what multi-rocks is and how it helps. So, as you know, TiDB is an OLTP and OLAP storage. It uses raft or consensus, and that's what gives it the data consistency. It has a fixed size of 96 megabytes per region. And this also is an important thing that I'll get to later. It has fault tolerance and it's across availability zones. So what is this region thing? Is it logical? Is it physical? TiDB treats it like a logical unit. But when you try and map it to the physical side, it's a bit fuzzy. Because internally it uses the region for load balancing, scale out, and even user traffic is partitioned by region. But there is no physical clear boundary. We have to scan all the SSTs to prepare a snapshot for a region. This leads to read amplification. Because they're all inside one RocksDB, that is the main thing. You have to scan the SST files in the RocksDB instance to figure out what the unit you're looking for, the 96 megabyte. Then several hot regions can easily trigger compaction in RocksDB. So RocksDB is LSM, and compaction is extremely expensive. That's the price you pay for using LSM. So it defers a lot of work, but in the end, you have to do compaction to delete old records, purge them, do that sort of thing. And it can lead to very large data sets per RocksDB, which can have very deep levels and very large SST files, very large files. And so as data sets grow in the 500 terabyte range, it magnifies the problem and makes it even worse. So certainly a compaction kicks in and it starts affecting all users of that node. And a few hot regions can impact the performance of all regions. Then we also found as the data sets became larger and larger, the LSM compaction increased the write amplification. It impacts the latency and jitter. This is what affects user queries. It lacks I/O isolation because everything is inside the same instance. The other thing that we found was that write throughput is limited because it uses a single write group, and that write group is a RocksDB implementation detail. We have no control over it. So to scale, both scale out and scale in becomes problematic. With too many regions, in the TiDB architecture, we have the thing called PD, which was in the reference diagram. It has to keep track of the region, so it has a heartbeat. So millions of regions means millions of heartbeats that it has to track, and that causes its own problems. I'll get to how that improves. So there's a lot of pressure on the placement driver, which is basically the metadata server of TiDB. So now this is that same diagram, but with multi-rocks on the extreme right. So if you look at the extreme right box, you will notice it has this thing called tablet. Each of these is a separate instance of RocksDB, and that is where multi-rocks gets its name. So it has multiple RocksDB instances per TiKV node. How does that help? Firstly, it unifies the whole idea of a logical and physical partition. The size of a region is no longer limited or fixed at 96 megabytes. It can range up to 10 gigabytes plus. Think of it as you have cold data, you don't really update it, so you can have very large regions. The hotter the region, the smaller its size. What that implies is it will split very eagerly. So it has a very eager split design to reduce contention. intuitively you would think if you have multiple RocksDB, it's an engine inside a TiKV. Each RocksDB must use its own write-ahead log, so your write amplification should increase. But no, some clever things have been done, and we don't use the write-ahead log of RocksDB anymore. We use the raft log. So the recovery takes place from the raft log. So the complete write-ahead log of RocksDB is eliminated. It's a huge improvement. The metadata for the column families is also moved up into the raft engine. There was no change in the SST data format. There shouldn't be one. And so it's compatible with the old version. So it probably have an impact on migration. So what are some of its other benefits? Because of the reduction in heartbeat, because you can have larger regions, so you have fewer number of regions. And that's where your heartbeat cost and the pressure on PD goes down. And that was, I believe, in some very large installations, a source of, it was a bottleneck, a source of contention. You also have better control per region. So you can shape your traffic and get better quality of service. The third point was also another bottleneck. So now you have one RocksDB and you're applying changes from the raft log. And you're using the same RocksDB write-ahead log, and so there's contention there, and it impacts everything. Now you have multiple RocksDB, you can do applies in parallel. That's a huge improvement in its performance. Snapshot generation is very cheap, and it's fast. Throughput is predictable because the granularity is much smaller, and you can shape the traffic. You naturally get a hot and cold data separation. So let's say you have large files that, because there's not that much contention, and so they're much larger, and you can move them to S3. Physical isolation, so you have more control, as I mentioned about the QoS. So you can also have translate that from the higher level, like the table, database, or user, and you can shape the traffic accordingly. And in the next section, I'll discuss a little bit more about that. It does have a little downside to it, we noticed in our tests. We are working on this. So you notice that prepare, this is a large AWS test. So the prepare phase, it's almost 4 times faster. Insert, it's 30% faster, I suppose. No, 131. So point select, read it was a bit slow. And this was due to too many small files at the L0 level. So we did some work on that. And then we tested with a slightly larger data set. And we noticed that it improved even the reads. But this is an area that is still being worked on a little bit. And we expect to see some improvement here too. Now I'll get on to the resource control. Resource control is important for providing QoS to your application or your users. People like to consolidate that. You don't want to have too many clusters running, so you want to consolidate them. You want isolation between applications. You want isolation between queries, for example, short queries, fast queries. So I'll talk about the detail now. So firstly, you want to have control over the flow, how the load is moving through the system. And for that, you need some kind of resource quota to control it. And that's what we call the resource group. You want the 2 resources that you're most interested in are the CPU and the I/O. So that's what we segregate on. We would like a fine-grained abstraction over which you have control and which you can modify and allocate. And that's abstraction is called a resource unit, which I will go into a little bit of detail later. And we want to track how those resources are being used so that we can do micro adjustments and smoothen out the traffic the way we feel, or we can plan ahead and do those sort of things. So let's take the case of having multiple applications running on multiple clusters. Your cost increases. They're harder to maintain. It's even more difficult to do data joins across databases because they're completely independent clusters. And people more and more want more consolidation on these things. not just from reducing cost, but also operationally from the access to the data. So you consolidate, but now you will have these things interfering with each other. And that's where resource control comes in. So if you have resource control, you have better quality of service. Change disaster, what does that mean? In this context, it means that let's say you suddenly get a spike, somebody runs a query, a runaway query, make some change, and it consumes all your resources. This will impact everything. You can limit that. You have controls on how you can mitigate all these problems. And it's a big deal in production for very large clusters. You don't want different loads or queries interfering with each other. And you do all this through the TiDB resource control. And I'll go over the SQL and some syntax and to show how it all works. Let's take this as a reference application sort of thing. You have an account service, an inventory service, and a shipping service. And each of these is, let's say, running on a different database. You want to consolidate them into one. The two diagrams at the bottom, on the right-hand side, we can think of them as different applications or users that we need separated and we can control over. And on the left could be a single application, but we want to distinguish between short queries, small updates, large batches, ad hoc queries, backup, auto tasks. These all consume massive resources. So you have control over the entire spectrum. So you want to manage multiple workloads in a cluster. You want to isolate, manage, schedule the access to the resources in the same cluster. So how do we do it? Or what is a resource group? So at the high level, think of it as a resource group. And the resource group is made up of a CPU and an I/O. And the three important options for each resource group are the rate of the backfilling. And this is something specified at the start, which I'll show. A priority, where the default is medium. And the third is burstable. This has two benefits. One is if there's, let's say you have some kind of naive system, just imagine you have a naive system in which you equally distribute the resources. But there is only one query running. You don't want it to use only its little slice. You want it to use the whole thing. So you can make things burstable, where it says, okay, use everything you can. Or there are queries or loads with very high priority that they cannot be blocked, but you're overcommitted. They must run. So you can tag them as burstable. So how does this all sort of work? So the high level view is the abstraction that we have is called a resource unit. And the scheduling strategy that we use is mClock. mClock was published in a paper by VMware. And it is a weight and constraint based scheduler. And I will read out from the paper itself. It's a constraint based scheduler that ensures that tasks receive at least their minimum reserved service and no more than the upper limit in a time interval, while the weight based aspect of the scheduler allocates the remaining throughput to achieve proportional sharing. So it handles both cases and it allows burstable loads too. If anyone wants to discuss this paper afterwards, I'm quite happy to discuss the details. I just don't want to go into it right now. So how do you use it? So you can either estimate the capacity using the mechanism that TiDB provides you, which is like there's a default, you do calibrate resource, or you say calibrate resource based on some workload which is predefined, for example. Or you can say calibrate based on the workload between this time and this time, and it creates the RU quota for you. So it can do that automatically, or you can specify it yourself, or you can say, I want it to behave like it behaved in that time period. How do you manage them? So SQL syntax is there. You can create a resource group. You can tag it as burstable. You can alter the resource group. You can make the priority high, low, medium, change the RUs. You can drop it. You can look at how it's being used through an information schema view. So you have very fine-grained control over it. So you can bind resource groups at 3 levels. It's a hierarchy. At the user level, at the session level, and at the statement level. And as you go lower down in the hierarchy, it overrides the one above. So you can say, for this user, I want to use this resource group in this way. But let's say you go down to the statement. You can give it a hint in the query that this query I want to be burstable, for example. But I want this resource group, or use that resource group. So it gives you an extreme amount of control. So this is a very high-level diagram. I won't talk too much, but I'll try and explain at the hand-waving level how it's supposed to work. So the placement driver, which is the metadata server, has the token bucket server. That's where all the data of how the resources are being used are stored. And it's also the global admission. TiDB tracks the CPU usage and has the local admission, which it uses to calculate where the session or statement or whatever is at. The actual action takes place inside TiKV. That's where the scheduler sits, then clock scheduler. So after a query has gone from TiDB into TiKV, depending on the context of that query with respect to the resource group, it will do the magic. It will do what's expected of it. So if anyone again wants to discuss this, please feel free to ping me after this. The third is the online DDL. So I want to compare it with MySQL because I'm familiar with the MySQL. In fact, the last big change in MySQL DDL, I actually wrote it in InnoDB. So I'm extremely familiar with this part from the MySQL perspective at least. So when you do MySQL DDL is single node, which is very different from a distributed DDL. And MySQL uses a mechanism inside the server, which is called metadata log, which is really a data dictionary log. So the way it sort of works at the high level is, when you start, the thread that starts the DDL, it will acquire a shared data log, shared MDL. Which any transaction that, so basically blocking all of the alter DDLs. And DMLs can progress, they all acquire a shared log, and they go and make changes. And the changes are concurrent in MySQL on single node, no problem. And it also has very good instant DDL in the last few releases, no problem. But when the changes, the DDL finishes, let's say, or an add index, when it completes and wants to do the switch or externalize or publish the change, it has to escalate that metadata lock to an exclusive lock. That is where the problem starts. If it's a heavily loaded server, all active transactions that have a shared lock will block the DDL transaction from upgrading to the X lock, and it can time out. That's problem one. Problem two, replication. This is single node, assuming. But nobody runs MySQL in single node. Everyone runs it with replication. Maybe there's some people do. With replication, the problem is worse. Up to 8.23, I think, MySQL would do the externalization, not release the X lock, and then send the bin log to the replicas, which would then run the DDL, and then it would be released. This increases the lag. It was improved in 2.7, I think, where they took the use case where you can group replication. I think you can specify eventual consistency, where it can send out the DDL before it completes. So then it sends out the DDL to the replicas. The replicas will start the DDL in parallel, and it releases the X lock. But then eventually, and only in that specific case, it's a little bit better, but not fully better. Distributed databases are very different. Why? So let's say you have, I don't know, 3 TiDB instances running, and you have different clients connecting to the 3 TiDB they can go to any of the data nodes. Whereas in MySQL, you can only write to the write node, and the readers will only go to the read node, because there is no consistency across a write and read, because there is a queue, which is the bin log in between. But here, you can go to any node, any data node. So they must all look consistent to the end user. That is the challenge. So you can't afford a synchronous update. You can't say, okay, on this TiDB node, I'm going to block everything, and that's it. And no client is allowed to connect to that. Eventually, you will lock all the nodes. So you can't afford that. You want to do it in stages. You want to define some mechanism where you can say, okay, I can see this version, and it's compatible. So this algorithm is based on the Google F1 paper. So it's a proven algorithm. You don't have to think too hard about it. Somebody else has done the hard work. You just have to implement it. So how does it work? It's a little involved. We can discuss it later. But you have to make the changes everywhere, and you have to copy the entries everywhere in all existing rows in the table. So you version the schema, and you have some constraints on how you can access the different versions. Those constraints are tied to the substates. So when you transition from, I think, the 4 substates, when you transition from one to the other, you define which DML operations are possible in this state. And the ones that any DML operation that is not allowed in that state is rejected. So the query will fail rather than block. So as an example, I think the first state, from none, when you go to the first state, you can only do deletes. And each version is compatible with the previous version. So if you're in state X, it will be compatible with the previous one. There are a few exceptions, but the paper, you have to read the paper to get the full detail about this, which I won't go into. So you want to go from the start state to the public or external published state, where everyone sees the same schema. So that is the algorithm that this uses. So versioning is what helps us get from the start of building an index to the end. So we did some tests, very encouraging tests. So you'll see it's got some config parameters. And we did the test over 100 million rows, 1 billion rows, and 5 billion rows. The improvement is staggering, in my opinion. It really is impressive. It's like 10 times. And there's a lot more work that is being done on this. This is not the end of it. So there's more parallelism coming and all sorts of other interesting stuff. We also did a comparison against other distributed databases to see, are we on the right track? And the higher the bar, the better it is. So it's much better than TiDB, the previous TiDB, which is the improvement that we've made. And it's also better than Aurora and Cockroach. Last, I'll talk about our product map. I won't read out all the details. I'll just sort of highlight some of the interesting things. MySQL 8 compatibility, this is a huge demand for this. So we are working very hard on this. Multi-rocks, I've just mentioned, that's very important. So we are moving to, as Ed mentioned, petabyte scale. This is also incremental backup. Integration with other systems, so improving CDC integration. A new optimizer framework, and along with that, some plan cache enhancements. And basically, background job resource control, which I did not mention, sorry, in my slide, but background jobs are currently, they're not implemented, everything else is, so this is also being worked on as I speak. So this is basically what I had to share with everybody. And thank you very much.